Hello and welcome to the Landwards Conference 2020 on lean principles and resilience in agricultural engineering. My name is Andy Newbold, and as editor of the institution's Landwards magazine, I am your host for today, and I am joined by an eminent fellow of the Institution of Agricultural Engineering, Dr. Mark Cooper. So Mark has a particular interest in health and safety, and he really wants to talk to us today about some of the things we're not sure we know about. So I'm going to leave you in Dr. Cooper's capable hands, and off we go. Over to you, Mark.
Well, welcome everyone. I've got a few thoughts that I've had over the last few months, basically around COVID-19 and the effect on businesses, their resilience, and the ability to perhaps withstand other events in the future. So my talk is called or entitled The Impact of the Highly Improbable. And as you'll notice there, the Black Swan. And Black Swan events have been around for a while and came to popularity, and I'm going to show one of the two textbooks that I'm referring to. The Black Swan by a guy called Nicholas Talib, and he is basically interested in highly improbable events and how we can be robust against them. The other book that I'm referring to is Learning from Disasters. This is a management approach by a guy called Professor Brian Toft and his colleague Simon Reynolds. And the concept of Black Swan events is based around this, that in our society today, we have a high reliance on what is called Platoism. Platoism being this idea that we can analyze everything. Everything can be looked at, decomposed, predicted, and so on. But we all know that there's a difference between what is called map and territory. We can model things, and I'll talk a little bit about that in a few minutes, but the idea that the map is the same as the territory is a fallacy. The map is only a representation. And so in trying to map things and model them, and that's the basis of a lot of engineering, we miss out a lot of the fine detail. And sometimes it's in the fine detail that these Black Swan events occur. So what are the characteristics of a Black Swan event? First of all, they're highly unexpected. They have a huge impact. And rather interestingly, people believe that with hindsight, they could have predicted that they would occur. So the classic example being 9/11. So if you go through those in detail, in numbered order, yes, 9/11 was unexpected. But I note that it's unexpected in terms of those people doing the analysis. It wasn't unexpected in terms of what the terrorists thought. They could foresee that this was a possibility. So unexpected in terms of those looking at and analysing the issue, clearly a high impact, and as we saw with 9/11, a great deal of hindsight that we could have predicted that those particular individuals were trained to be pilots and had no proper use for their piloting skills, etc., etc., etc. So those are three things that we look for: highly unexpected, big impact, and then there's this sort of hindsight bias. We look back and believe that we could have predicted these events could have occurred. So Platoism, something that we as engineers do quite a lot of, is looking at the theory of forms and concepts. So we are inundated with forms and concepts from how electricity works, mechanical strengths of materials, etc., etc. So engineers, scientists use these theories and forms quite a lot. And as we all know, they work most of the time. And Black Swan events are really talking about those occasions where we haven't predicted, our models don't quite work. Those are situations that we're interested in. And they're the highly improbable but high impact matters that we are concerned with. Now, there's been, for a little while, Donald Rumsfeld has come up with this, or is famous for talking about, there are known unknowns. And this is the idea that we have different degrees of knowledge about the world that we live in. And these are summarized in these rather clumsy, but actually quite useful descriptions. And if we take the first one, the known knowns, well, that's where we feel comfortable. This is the well-known and tried principles that work. Fair enough. The known unknowns. These are identified gaps in our knowledge, but we know we don't know them. For example, if we look at COVID, we can imagine that we've got some idea that COVID transferred across the species barrier. So this is the zoonoses from bats to humans. We believe we know that. The exact detail of how that happened, how that mechanism occurred, we don't know. But that makes it an area for future research. But that's where we sort of classify, there's a little grey boundary. We don't know those particular things, but we're going to go and find out. And the nature of research is these known unknowns, eventually, when we understand it fully, what happens? They become into our domain of knowledge, they become the known knowns. They're things that we now understand fully. Next one, the unknown knowns. So the best way of describing that is it's known to mankind, but not necessarily to those making the inquiries. So these are concepts that if we were to ask the right people, they'd be able to tell us. But if you were working from first principles, the blind sort of a way, then you may not understand it. So this is where we use a judicious use of expert knowledge. People out there who do know that that's their specialism, we just have to find them and extract the knowledge from them. So a good example of that, the French train operator SNCF, they basically built 2,000 new trains at vast cost, only to find that they were too wide for many of the regional platforms. Clearly, if you'd asked the right people, the district engineers, they would have been able to tell you the size of the platforms and would have been able to tell you that those trains wouldn't have fitted. So asking the right people is how you really deal with that, the known unknowns. The unknowns. So, are we able to stop, Andy?
One, resume.
So the unknown unknowns are the areas where we don't really understand, we're unaware of concepts, and it's the area of new inventions. So as an example, the internet at one stage was unknown, and as people discovered it, it was new discovery, it becomes part of our general knowledge and general understanding. But there's always going to be things that are outside of our expertise. If we apply this down to a sort of a product level, whenever you make a change, whenever you introduce a new aspect to a design, a completely new change in the way that you do things, there are inevitably going to be things that you don't understand fully. Your Platoism may let you down. Your model may not fully give you the understanding that you need, which is why in many risk areas, change analysis is actually one of the most important areas where you look for risks, because that's where you change, you make your changes, your understanding is incomplete. And that's where the big risks and the big problems are. Take, for example, banks, and in their computer systems, they're making changes, and guess what? We all can't use our card machines for days on end. That's an example where the knowledge was incomplete for the change that they were going to make. So change analysis turns out to be a really important area if you want to look for Black Swan events and high risk issues. I think we all are aware of the Boeing 737 MAX. This was grounded worldwide because of a new maneuvering system that was introduced that behaved counterintuitively for the pilots, that caused them actually to crash unnecessarily because of the way this design was introduced, its characteristics. I'll come back to this later on when you look at airlines who've just got one particular type of aircraft and the effect when you have a problem, the effect that has on their or your business. The other concept that I was trying to introduce is a little bit about isomorphism. And this is the idea that systems, whether they're biological, sociological, or mechanical in origin, can and do display similar characteristics. In fact, you can describe them as basically the same kind of system. So the way in which the human body deals with viruses, for example, and how computer systems deal with viruses, they are completely different, but behave in similar ways. So a biological system actually has similarities with a telecommunication system, and that we can draw lessons by looking at one that are useful to the other. One in human characteristics is called, interesting one, is the latent pathogen. Something that exists within a system and has been there probably since birth, human system, since birth, and then given the right conditions, manifests itself as disease. And the exact triggers for it are not known, which is why we call it latent, it's hiding there, pathogen, the capacity to do harm. Well, I'm sure we can all think of examples of systems that we've been involved in, pieces of equipment that we've been involved in, where there's been a fault and it only manifests itself at when some very specific form of conditions arise, and it comes as a shock or a surprise to us at the end. So the two corollaries to this isomorphism. Firstly, any failure that occurs in one system can have a propensity to occur in another. This is looking across, looking for things to happen in similar systems and thinking, could that happen to us? And I just alert you to the fact that with COVID-19, are there ways in which failures like this from another country can travel very, very quickly through and give great impact to us? Could that happen with other systems, mechanical, electrical, software systems? Could that happen where we import something that spreads very, very quickly? So that's the lesson from isomorphism. Secondly, two systems may appear to be completely different, but if they possess the same or similar components, they could be open to the same, what's termed common mode of failure, type of failure. So those are just 2 points to reflect on, that COVID actually, and SARS and these other diseases, are there ways in which we can import systems and components that have failures in them, import those and cause problems in the UK or within the designs that we're interested in. So a point for reflection, I think. are just some examples. In biology, similarities in different types of organism, different types of algae show similar characteristics. In chemistry, the crystal structure of components can give you of compounds can give you perhaps some prompts as to how chemical materials may behave. In sociology, similarities in different processes and different organizations may actually carry across. So at the beginning, I talked a little bit about Platoism and this idea of models and characteristics and concepts that we're all familiar with. Any model is a simplification of real life. That's its purpose. Its purpose is to turn something quite complicated and sophisticated, difficult to understand, into a form, shape, diagram that we can all understand. And these are quite often called shareable models, exactly for that reason, because it allows individuals to talk with a common basis, talk about quite difficult concepts, but in a simplified way. Quite often, these shareable models are graphical representations. They appear everywhere. They can be conceptual. Those of you involved in quality will quite understand plan, do, check, act. That's a very high level model. Other examples, block diagrams, which we use in reliability. Those block diagrams, great, fine, dandy, but they don't tell you about necessarily how those particular components, pumps, for example, behave under different temperature conditions, let's say. They're just a gross aggregation of what their reliability and performance is. Different environments, different working conditions actually can change those figures. But there's an illusion, a belief that they represent the real thing. So this is a map, but it may not represent the dirty, greasy territory where these components live and work. Again, the same electrical circuits don't necessarily replicate similar things of how they behave with temperature, different working environments, different suppliers. It all can change greatly, but these are meant to be simplifications, and they're very useful simplifications that work most of the time. Hydraulics being the same, both those diagrams on the left and the right represent the same piece of equipment. One is a hydraulic circuit diagram, one is much more of a schematic. They're both the same component that they're trying to talk about, they're just represented in different ways. And different models and different approaches can give you different representations. It doesn't make them wrong, it's the same cake, it's just cut up in a slightly different way. But it's that point that I'd like to really emphasize. They are the map, they are representations. And whilst they serve us well most of the time, they are not perfect representations. And it's where they don't work, aren't a full representation, that you have the potential for these Black Swan events. So I suppose we now talk a little bit about quality and standard deviations and representations. And most of the representations that we have in statistics, we will take measurements and we will come up with a standard bell curve to show that's how a particular process works. And we use the plus or minus 3 standard deviations, or sometimes with quality 5 standard deviations. But what it means is our model, our representation here, represents 99.7% of the occurrences that we've been able to measure. And in most circumstances, that is good enough. But what happens about these very low frequency events, things that happen at the tail end? So there's 2 tails here, tail at the bottom, tail at the top. Those represent 0.3% of all the data that you might think that you captured. But there's the unknown. And just every now and again, you get problems where at the long tail side of things, Black Swan events live. As I think has been said, looking in the corners, that's what we're suggesting. You need to look in the corners. And it's at those very rare events, but when they do occur, the consequences can be huge. And that's what distinguishes a Black Swan event. So how does that relate to resilience? How does that relate to being a lean organization or having lean processes? And the answer from the 2 books that I recommended, the key answer is to be resilient to these Black Swan events, you need to have diverse systems. Now that goes a little bit against what many organizations believe to be lean. So diverse being different types of pieces of operating equipment, so that if one breaks, you've still got the other 2 operate. So the classic being airlines, Ryanair, EasyJet, and so on. Other airlines do exist. They actually only operate one type of aircraft. And the reason they do that is they only need pilots trained to use one piece of equipment. Their maintenance schedules, their maintenance setup is all used for that one type of aircraft. What happens though, as within the 737 MAX, what happens if you've got a problem with that one aircraft? If you're wholly reliant on it, you've got this idea of common mode failure. Everything goes down. If, as some airlines operate, you've got different types of aircraft, it gives you a bit more resilience, because if one goes down, you can still keep operating. So this is the idea that you reduce the opportunities for this common mode failure. What also is known, if we look at nature, look at wisdom, well-established technology is the one that we prefer. It's the most reliable, it's the most resilient, or can be the most reliable. We know what we're dealing with. And it's all very well in manufacturers' tests, people predicting that there is a failure of this particular component once in every 20 years. If the component hasn't been around for 20 years, you are speculating, you are testing, you are anticipating how a component would work. It's not quite the same as a component that's been around, proven, tested. So well-established technology is actually something worth looking at. Redundancy, again, in the lean way of thinking, we might be looking at reducing the amount of redundancy, but redundancy can serve a purpose. 2 generators in parallel. If one doesn't work on startup, you have another. So there's a cost to that, and it isn't lean, but if you really want high degrees of reliability, then that may be what you're after. The use of low cost, moderately reliable components in parallel. We've all done the sums, and you can actually end up with highly reliable systems made up of not terribly reliable individual components, but lots of them configured in the right way. Multi-purpose components. So that's always helpful. So I have at home a mobile battery charger. It's brilliant because it's also got a 12-volt cigarette output and a light to it. That's just an example. The idea that something, a particular component, serves multiple purposes so that you don't, well, it gives you resilience in any way. So my message, if there is one, it's to think a little bit about how could you be affected by one of these black swan events. And just remember the key thing, black swan events by their very nature are not reliable. So if you start sitting down trying to list all the possible scenarios that you might think of and how you would deal with them, you're on a hiding to nothing. That won't help you with black swan events. What black swan events, if you really want to be resilient, you don't know what the event is, but how could your systems recover in the event of an outage for whatever reason? So you don't think so much about, don't concentrate on how the event would occur. You concentrate much more about how could your system rebound and be resilient to that sort of event that you don't know, you haven't predicted, you can't predict what it would be, but you've got that built-in resilience. So that is my main message, really. Look in the corners and think of resilience and be mindful of that when you're trying to be lean.
Mark, that is excellent. Thank you very much. We are still recording, so obviously my first, I feel as an engineer that I should be able to see all the possible outcomes. So it is sage advice for me to say, stop worrying about what might happen and start worrying about the resilience in your system. Because again, being task orientated, we like to think that we can see all the possible outcomes.
Yes.
Whereas the reality is in the corners, we can't.
I think so, that's exactly right. It's this idea that, you know, we overanalyze things and we try and predict all the possible outcomes. And that is the point, that you can't predict because these are unpredictable events.
And we find ourselves living through one at the moment with a series of completely unplanned and unintended outcomes. And as you know, the ag engineering industry has found, in some cases to its peril, but in many cases, a lot of inbuilt redundancy and a lot of inbuilt resilience in systems has come to the fore for a circumstance which nobody planned for, because global pandemic was not on anyone's list.
And, you know, if I can think of an agriculture engineering example, a lot of the software for things like round balers, as a for instance, comes from one source. So whoever you go to, you end up with software from a particular individual's company. Nothing wrong with that, other than it's a potential for common mode failure. The same if you have the same components come from a particular country and there are problems with the quality of that. And I think we've seen that in telehandlers, for example. Some of the components have been outsourced and you then end up with a problem because you've now embedded something into your processes and your equipment that causes you problems.
Yeah, or in blunt terms, you can't get them because the factories which were making them, be they in China or be they in Italy at certain times this year, the factory shut down or the supply chain shut down, and through no fault of your own, because your actual production facility was based in the UK or somewhere which wasn't affected. It all had a knock on which stretched a lot of things earlier this year, didn't it?
Yeah.
I think, Mark, just to say thank you very much for your anybody taking part. There will be a live Q&A via Zoom on Wednesday, the 4th of November from 11 a.m. So if you'd like to, rewind and watch this presentation again and work on your difficult questions for Dr. Cooper, I am sure he will be thrilled to be available then alongside all of the other speakers from the other presentations. So don't forget, go back to iagree.org and get your login details for live Q&A on the 4th of November, and also possibly listen to other presentations which will be live and in some cases are already live now on the IAGRE's website. So once again, Dr. Cooper, thank you very much, Mark, for a most insightful presentation, and it's helped my mind go slightly sideways in things here as well. So, thanks for the stimulation, and we'll look forward to seeing you on the 4th of November. Thank you, Mark.